Okay, hey everyone. So we're going to finish the lesson on ray diagrams and concave and convex mirrors. We started this one on Tuesday, which is actually when I'm recording it. So I'm not sure. We might cover some stuff on Wednesday. Your yesterday, my tomorrow. This is weird. If we covered any of these slides after the test yesterday, just skip ahead in the video until you get to the point where we're at, okay? But on Tuesday, we left off on concave mirror diagrams. So we drew, those were the steps of drawing them, remember? We're going to do the first ray parallel to the principal axis, then hits the mirror, reflects through the focal point. Second one goes through the focal point, then reflects off of the mirror parallel to the principal axis, and then we draw the image where the rays intersect. Okay, so we did this one together on Tuesday. Okay, found that it made a real inverted smaller image. Now we're going to try this one where the object is between 1 and 2 focal lengths from the mirror. Okay, so I don't know. I don't think I can draw. I don't think I'll have a ruler here. So I'm just going to do my best, okay? I'm trying to use our phone, okay? So remember, if at any point you need me to, or you need to pause the video to copy down anything, go ahead, and I'm sure the supply teacher will let you do that, okay? So here, F, remember, is our focal point. This is our object. We draw like an arrow just because it helps us see whether it's still upright or if it's inverted. Okay, so our object is there. So we are going to draw 2 rays. The first ray starts at the object, or it comes from down here. Wait, where am I drawing? Is there blue here? I should probably have planned this earlier. This could work. Okay. Here. Okay. So what you do is you draw. Oh, why'd you do that? Okay, we're drawing a straight line to the mirror. Then it's going to bounce off of the mirror. Oh God, how am I going to do this? I have no idea what the angle is going to look like here. Okay, this is. Okay, so it's going from here to. Okay, bounces off the mirror. And goes through the focal point. Oh, I missed. Okay, we'll do it freehand. Bounces off the mirror and goes through the focal point and then keeps going on forever. Actually, isn't too bad for freehand. Okay, so remember, this bit here in the gray is our mirror. This is ray 1. Okay, so here is our mirror, and that's our focal point. So the first ray goes parallel to the principal axis here. Principal axis. Bounces off the mirror and gets reflected through the focal point and goes on forever. Okay, ray number 2 goes from the object through the focal point to the mirror and will come from somewhere over here. Ray 2 bounces off the focal point and then goes straight parallel to the principal axis. Okay, so let's do one arrow kind of near the mirror to show that's coming in this way, then bounces off and keeps going on forever this way. Okay, and then we draw our image where the 2 points intersect. So right here, got a triangle and the line. Now, it might not be as perfectly thick as the original object was, but it's all approximate. So this is our image down here. So what you notice right away? Well, first thing you notice is that it's upside down or it's inverted, like the last one was. Okay? It's made from two solid lines, so it's going to be a real image. And I think it comes through pretty clearly here that our image is bigger than our object. Okay, the object is only from here to here. Where's the laser pointer one? Laser pointer, yay. Goes from here to here. Image goes from here all the way down to here. Okay, so even though it's upside down, the type of image formed is real because it has the two solid lines. It's inverted because it's upside down, and it's bigger than the object, okay? Just taller. Okay, so if the object is between 1 and 2 focal points from the mirror, it will be real, inverted, and bigger. Unlike this one that was real, inverted, but smaller. Okay. On to the next. So if the object is right at the focal point, if it's right at the focal point, the light can't really go through the focal point. So you'd be able to draw ray 1. Back right through the focal point. And it would start somewhere back here. Ray 1, hit the mirror, and go off forever. But you can't have one that goes from the object right through the focal point, like that. Nothing's going to work. So anywhere you try to like have it bounce, it's just going to reflect kind of away. And you're not actually, sorry, they come off parallel. That's not a good image. It's actually going to hit and just bounce off parallel to this line. Okay, so these two are parallel. Right, two. So they're never actually going to touch each other when the object is at the focal point. So therefore, no image is made. Okay, because these lines, let's go to black, are parallel. If the lines are parallel, they're never going to touch. They're never going to cross, okay? So you're never going to have an image made when the object is at the focal point. Okay? So we've had an image that's real, inverted, small, real, inverted, big. We've had no image made when it's at the focal point. Now let's talk about when the object is between the focal point and the mirror. Okay? Hi. Yes, Nathan, I'm making your lesson right now. You'll hear this on Thursday. Okay? So the first one, remember, comes here. It's going to bounce through and reflect through the focal point. Not great, but you can kind of get the gist of it. So that would be ray 1. So remember, it comes in parallel to the principal axis. Oh, I forgot to label the object in the last one. Sorry, that was object. So we're going to come back to this one in a minute as well. Object. I don't think I spelled that right. Object. There you go. You get that's the object, and this was the principal axis. Okay, so ray 1 comes in parallel to the principal axis, bounces through the focal point. Ray 2, I should go into a race where I have object just because I have to write through it. So it's going to come through the focal point to our object, kind of like that, actually. Okay, then come through like that, hit here, and then bounce back, reflect off parallel. Like that. So that is ray 2. I just want to make sure that I'm drawing this correctly. Is that to the right? Okay, so this one that comes through is here, bounces off. This one comes through the principal axis, comes off. The reason we have to draw this ray 2 but from the bottom is because it's inside the focal point. Okay, but what we're going to do is so like right now they're crossing at the focal point but nowhere else. So right now it's not making an image, but it will on this side, because if we take this reflected ray here and just extend it with a dotted line, and we take this reflected ray and extend it with a dotted line. Okay, so kind of looks like the light's originating from here. Okay, so this ray is being extended that way, and this one's coming in, going straight through that way. Okay, so what we have over here, our lines intersect. What? I don't think that's any kind of color. Is this black now? I don't even, yeah, there we go. And we have our image over here. So our object and our image. Okay. So I remember Elizabeth was talking on Tuesday about what makes an image real versus virtual. Whenever we have to use these dotted lines to make the image, that's when it's virtual. Okay, so because of this, we have a virtual image, but the image is upright because it's facing the same direction as our object, and it's also bigger, because you can probably see that it's bigger. So what we do is we extend the reflected lines, the reflected rays, okay? So that's our incident, that's our reflected, extend the reflected one. That's our incident, that's our reflected, extend the reflected one. Okay, that makes an image behind the mirror, which makes a virtual image. That's why it's virtual. Because it looks like the light's originating from inside the mirror, even though we know there is no light source in the mirror. Okay. The reason why we can't make an image over here is because these two lines are never going to touch. If they're parallel here, we extend the reflected ones back. Or this is back on the last one. It can't make a virtual image either, because even on the mirror side, they're still parallel. Not parallel. Parallel. Okay. So that's why it can't make it on either side, because the reflected rays are parallel forever. Here, they're not parallel, so we can extend the reflected rays back, okay? So reflected ray, and this one is also the reflected ray. Okay, so only extend the reflected rays. Okay. I know that might be a little bit confusing, but because they're only crossing over at the focal point, that's why you can't have an image there. But if you were to look at like a spoon, like the inside of the spoon, your face is upside down in it's in a fun, like in the spoon, it's upside down because you're kind of looking, you're beyond the focal point. As you get closer, so here we had a real image that was inverted and smaller because the focal point of a spoon is very small. If we were to get close enough, it would actually go upright. And then here, it would actually start to get even bigger too. Okay? But if you look at like a funhouse mirror, the ones that are like concave, you look bigger in the parts that are kind of stretched like that because you're within the focal point of it. Okay? If you're to stand outside the focal point, you make a real image that's smaller. Okay? So you're going to have a worksheet today to practice making ray diagrams, and it'll probably help with this, okay? So let's just move on quickly to convex mirrors. So a mirror with a surface curved outwards is a convex mirror, also called a diverging mirror, okay? So it's curved outward like that. So concave kind of came in like a cave. This one goes out. And it's called a diverging mirror because it diverges all the light rays, okay? Converging, all the light came together at a point. Diverging, they all diverge out, okay? So instead of collecting light rays, it spreads out the light rays. And it spreads them out because the focal point is behind the mirror, okay? So your focal point is actually within the mirror, okay? It's just behind it. So if you were to extend all the reflected rays, they all come to a point at the focal point, but the focal point isn't visible if we were to use light, okay? So steps to drawing convex mirrors, they're really similar. So you do the first ray that's parallel to the principal axis, and then once it hits the mirror, it's going to appear as though it originated from the focal point. Okay, so it's going to hit, and you're going to have to extend the line from the focal point behind it. Okay, I really hope I did this diagram right coming up. The second ray travels towards the focal point like it's originating from the focal point, but then once it hits the mirror, it gets reflected back parallel to the principal axis and also extended virtually through the mirror. Okay, and then it's going to make a virtual image, and you draw that where the rays appear to intersect. Okay. So if the object is anywhere in front of the mirror, it doesn't really matter. You're going to get the same type of image. Okay. So again, first ray, always from the top of the object to the mirror, parallel-ish. I'll use a ruler, parallel to the principal axis. Okay, so here we go. So we have our object here and our principal axis, and here's our focal point. So our array is going to look like it came from the focal point, and then it'll go up that way. Okay. So ray one comes in and then gets reflected away, but the reflected ray lines up with the focal point. Okay, so that should all be a straight line. With your ruler, you can make it straight. If this program had any kind of straight line, I would use that, but I can't get it to work. Okay, so it should be all straight lines. Okay, so it looks like it came from the focal point. Actually, I'm just going to move my arrow because I don't know exactly where it's going to be. Okay. Ray number 2 comes in like it originated from the focal point. Oh God, this is going to be tough. And then it would have come. Yeah, that's close enough. Okay, so remember, don't extend the incident ray. You extend the reflected ray. Okay, so that will come in like that. Just line it up with your ruler, okay? So it comes in like that, and then it gets reflected back parallel. But it looks like it's coming from here. Okay, so look, the reflected ray looks like it's originating somewhere over here and just goes straight out. This one looks like it's coming straight out of the focal point. So where do these two lines cross? They cross, like I kind of gave away in the last slide, virtually right here. Okay, so here's our image. So because there are two dotted lines crossing, it's going to be a virtual image. It's also behind the mirror, so again, that's why it's virtual. Or just another clue that it's virtual. It's also upright because it's also going up, and then it is smaller than our object, okay? So the type of image formed is virtual, upright, and smaller. Okay, so this is true for anywhere in front of a convex mirror. Okay, all convex mirrors are going to make small virtual images that are upright as well. Okay, so just some quick applications. Concave, we have flashlights. So inside of the flashlight, where's my laser? Inside the flashlight here, it's a convex mirror or concave mirror. Okay, so it's inside, you have the light here, and then all the light kind of shines out, and then they all get reflected parallel out. That's why you get a straight beam of light with a flashlight. Same thing for headlights. You have the little light here that gets reflected back, and then all goes into a straight line. And with your headlights, you actually have them pointed down. So with your car headlights, they're actually pointed, if this is the light, they're pointed down so that they don't affect other drivers. When you put your high beams on, that's when you change them to being straight out, and that's when it can affect other drivers. That's why you only drive with your high beams once you have once there's no one else in the area. Okay, no other oncoming drivers. Solar ovens are actually used. You can actually cook food with them. Okay. So what it does is it's a concave mirror, but it focuses all the light in at the area that you're cooking. So it just increases the temperature here with the sunlight. So you can actually cook using this energy from the sun. That's it. Okay, convex mirrors are security mirrors. So those big round mirrors that you'll see in stores to help prevent shoplifters, just because you can see a large area in a small mirror. And then rearview mirrors in cars are also convex, just to allow you to see a larger area. Okay, and that's why objects in mirrors are closer than they appear, because it looks small in your mirror, but it's actually closer than you think. Okay, just one last thing to go through would be magnification. So magnification measures how much larger or smaller an image is than compared to the object itself. Okay, so we express magnification as a ratio of either the height of the image to the height of the object, or the distance from the image to the mirror, and the distance of the object to the mirror. Okay, you can use either way of doing it. And I forgot to put in the formula here, didn't I? Shoot. Okay, so I think you have some space there. So the formulas are either magnification equals HI over HO, so the height of your image, over the height of the object, or M for magnification equals di over do, distance of the image to the mirror, over the distance of the object to the mirror. Okay, so let's do two quick examples. The microscope produces an image that is 100 micrometers in height from an object that is actually 0.4 micrometers in height. Okay, so what's the magnification of the microscope? So first thing you want to do is write down what you have. So produces an image that is 100 micrometers. So, whoop, that's not distance. It is going to be height. Let's use blue. I like blue. Height of the image equals 100. This fancy U is called a micrometer. Okay? The actual units don't matter because I'm always going to give you the same units. Okay, just make sure that you have micrometer and micrometer. The actual units themselves don't matter. If they're the same, they're going to cancel out. Okay, the height of the object is actually 0.4. 40 micrometers. Okay, so what is the magnification? Well, let's just plug this into our formula. Height of the image all over the height of the object. M equals 100 divided by 0.40. The magnification, calculator. 100 divided by 24. 250 times. Okay, so the unit, it's not really a unit, it's just times because it's 250 times bigger than what it actually is. Okay, so therefore, the magnification is 250 times. Oh, magnification of the microscope. Okay, so really basic formula, but you can also rearrange it to find a different variable. Okay, like we'll see here. So an insect is magnified to 12 times by a concave mirror. Okay, so we know our magnification is 12 times. If the image is real and inverted and 6 centimeters from the mirror, how far away is the insect? Okay, so the image is, so DI is 6 centimeters away. So how far is the insect? We are looking for DO. Okay, so here we have M equals DI all over DO. Okay, now to find DO, what we do is you can multiply both sides by DO and then divide both sides by M, but what happens is we'll just switch those two. If you want to make a triangle, you can make a triangle if it helps you, but it's not good for your math if you go farther along. So to find DO, just know that you'll just flip those two. Okay? So distance of our object is equal to the distance of the image all over the magnification. Okay, so DO equals 6 divided by 12. So DO equals 6 divided by 12 is 0.5, and our units are centimeters. Okay, don't worry if you're a little confused by that. We'll go over it more Friday when I get back. But for now, I just want to show you. Okay, maybe it won't work. I'll show you on Friday then. Cool video about converging light. Okay, so that's it for today. There's a worksheet that'll help you practice your ray diagram and I think magnification calculations. But if you have trouble with any of those, we'll have some more time to do everything on Friday. Okay, but I hope everyone's having a good day, and I will see everyone hopefully tomorrow. All right, have a good one. Bye.